Okay, so welcome to this video on the first fundamental theorem of calculus. So in the last video we proved the second fundamental theorem of calculus, which is the one connecting integration to antidifferentiation. In this video what we're going to do is basically show that if a function is integrable, it has an antiderivative, which is the first fundamental theorem of calculus. Fundamental theorem of calculus. Oh dear, fundamental theorem of calculus. There we go, the first fundamental theorem of calculus. So, the first fundamental theorem of calculus, to just state it, is let f map the interval AB onto R, so onto the real line, so a picture. We have our closed interval AB, and on this we have some function. I've drawn it as a continuous function, but it doesn't necessarily need to be continuous. And let f be Riemann integrable. Then you can define big F as a function of x to be equal to the integral from a to x of little f of x. So integrate from a to some variable point x, and x varies from a to b. So x is less than or equal to a, is greater than or equal to a, and less than or equal to b. So it's between a and b. And basically the claim is that if you differentiate this function with respect to x, that it's equal to little f of x. Okay, so how do we prove this then? Well, let's take our definition of differentiation. So, the derivative is the limit of a quotient. So let's write out that quotient. So let modulus of h be greater than 0. H is some little real number such that x plus h is, I need more space, such that a is less than x plus h is less than b, is greater than, here. Okay, so basically what I'm saying is, when you add on the h, and h doesn't necessarily have to be a positive number, it can be a negative number, hence why I said modulus of h is greater than 0. So it's some number, but when you add it on, it has to be such that you're still within this point. And okay, we get some problems when we go to a or b, because we can't have negative numbers there. So at that point, we'll just take the right-handed derivative. I will assume that h is all the h's are greater than 0. And we'll just take the limit as h comes down from there. We'll ignore to the left because we don't know whether the function is defined on the left. And similarly, at b, we'll just take h to be negative numbers. But for all the other ones, there'll be a range of h values that we can take, some less than 0 and some greater than 0. But you should make sure that when you add h to it, that it still remains within here. Because obviously I don't know what the value of the function is outside of here, so we don't want x plus h to be outside of our domain. Okay, so f of x plus h minus f of x over h is what we want to find. And then what we want to do, so we'll get basically a little, we'll get some little domain of h. So this is, h will go down to, negative a minus x there. So this is basically what I'm doing, is I'm looking at the domain of h values, the values that h can take. So it can go down to a minus x. And the reason is that when you add a minus x to x, you'll get a. So all values less than that, you'll get something in within here. So that's the maximum value that you could take down here that would take you onto a. And similarly, up here, you can have b minus x is your biggest value you can take. So let's just... so this is our domain for h, and what we want to do is we'll plot this function here on this y-axis here, and we'll get some sort of graph like here, and it won't be defined at 0. This has no meaning when h is equal to 0. You cannot divide by 0. It's not algebraically definable. It breaks the axioms of field algebra. However, if it's differentiable, there will be a limit. We can take the limit as h approaches 0. We can say, effectively, if I come closer and closer and closer, what value do I get closer to? What value would it be natural to put there, even though we can't define the value at 0 by this? We could define the function to be this, where h is not equal to 0, and the limit of this when h is equal to 0. What would be the most natural point to put there is really the intuitive sense of what we're asking. It's almost like analytic continuation in complex analysis, if you're familiar with that, where you there's only one point that it could be and make any sort of sense, really. Be continuous. Let's construct this value then, and then we'll take the limit as h approaches 0. So the value of this is f of x plus h is the integral from a to x plus h of f of x dx minus the integral from a to x of little f of x dx, and all of that divided by h. Remember, h is not at this moment converging on 0, it's just some number within this little field of numbers that you're allowed. I don't mean field in the sense of field algebra, I just meant, this little set of numbers that we have. So now we use the properties of integration, that we can split this into this term here, into the integral from x to x plus h of little f of x dx plus the integral from a to x of little f of x dx minus the integral of a to x little f of x dx all over h. So obviously this bit cancels, and we are left with, and I'll just move it back into view, we are left with 1 over h, the integral of f of x, little f of x, dx from x to x plus h. Okay, so now we pull a sort of trick that's often used in mathematics, and I've done something very silly here. I have used the same variable inside the integral as is here. I should replace all of these dummy variables that are going to go with some u. So replace all of these with u's. So this should be u, this should be u, this should be u, this should be u. The reason is I just don't want to confuse you. It's not the same as this x here. It's a dummy variable. U, like that. Okay, so we're going to use a trick that often is used in maths. We know the answer. We have a conjectured answer. So let's sort of get that answer and then correct the statement. So let's say that this is equal to f of x minus f of x plus 1 over h, the integral from x to x plus h, little f of u du. So I've done nothing, I've done something, this is going to be very clever, but I haven't done anything too fancy here. You've added it on and you've subtracted it off. So nothing fancy yet, so I'm going to turn over the page and continue. So we have the f of x minus f of x, I'm just rewriting it back out, plus 1 over h, the integral from x to x plus h of f of u du. Du, not dx. Okay, so if we wanted to pull this in within the integral, this bit, we could write it as 1 over h, the integral from x to x plus h, f of u minus f of x, couldn't we? Why is that? So why is that? Well, f of x relative to u is not varying, it's some constant. X is now a set value, this is a constant with respect to u, so we could pull it out of the integral. And when we integrate it, all we'll get is minus f of x times how much this has changed, which is by h. And then you'll divide by h, so it hasn't changed at all. Okay, so if we now we wanted to prove that, so we'll remember this formula up here, that the derivative of, sorry, no, that's a big quotient. This is f of x plus h minus f of x over h. That is what that is. So we'll remember this big formula that we've got up here. This is going to be very important. But we're going to take a step back and ask what we wanted to prove in the first place. We wanted to prove that a limit as h approaches 0 of this big thing we've got up here, f of x plus h minus f of x over h, is equal to, what do we want to prove? We wanted to prove that it's equal to f of x. Okay, now what's the rigorous definition of this? This means that for all epsilon greater than 0, there exists a delta greater than 0 such that, and remember we're taking the limit around h is equal to 0, so I want delta to be within, this is my delta ball, so I want such that if modulus of h is less than delta, it implies that this is within epsilon of this, so that it implies modulus of f of x plus h minus f of x over h minus little f of x is less than epsilon. So that's a mouthful. So basically what I'm saying is to draw a picture. We have, what was this? This was x, no, this was a minus x, and this was b minus x, yes. So these were the values that h could take. So this is h, and this is our quotient. So this is f of x plus h minus f of x over h. So x is now some set value, and h is the thing that is varying. We're taking, so if we have this other picture up here, where we had, you know, our original interval a, b, you select a point x, and then around each point you have to take all possible h's, you construct this quotient, you get some function that isn't defined at h is equal to 0, and we're asking what is the limit of this value for this x, and then we will do it for each and every single x and work out what the derivative is at each point. So you've got to do this entire, you've got to plot one of these graphs and take the limit of it for every single point on this little interval here. That's what we're doing in effect. So we now want to take the limit of this function, and the limit is defined to be, well, we're saying that we want the limit to be f of x. We want this sort of point that it's converging to be f of x. So the definition of that is that if you take any epsilon ball around f of x, so this is now an epsilon ball, so you give me any epsilon greater than 0, I will take you a little ball around there, so all the values here that are contained within here, and I want you to you must be able to find me a delta ball around 0. You must be able to find me a delta. You must be able to get this close enough such that all of these points are mapped within here, and you can make this epsilon as small as you like. So basically what it's saying is, I want this to get arbitrarily close to here, so you have to be able to find me a point, whatever size I want, however close I want it to get, you have to be able to find me a ball around 0, such that all the points in that ball are mapped into this ball around f of x. So basically you have to be able to get this arbitrarily close by making this arbitrarily small. I have to show you that however arbitrarily close you want to get, I can find you a point after which you will be that arbitrarily close if you are within this delta ball. Okay, so that's what we're doing here. So we need to prove that that I can find you such a delta. So we're going to go to our convenient definition up here, where the f of x's will cancel. So if I replace this with this that we showed up here, I want to replace now in this term here this thing with this. So we'll do that then. So modulus of big f of x plus h minus big f of x over h minus little f of x is equal to, well, replace this thing with little f of x plus 1 over h x to x plus h of f of u minus f of x dx minus little f of x. So these now cancel here, and basically we are left with the modulus of 1 over h, the integral from x to x plus h of f of u minus f of x dx. And I have to show you that I can get that less than epsilon by making mod of h less than delta. So I want to evaluate what this is really, don't I? So that I can know what I need to bound. Have I got any more paper? Oh, how inconvenient. Found some. Right. So more paper. There, that's nice and straight. Okay. Okay, so we want to look at this modulus 1 over h x to x plus h of f of u minus f of x dx. Oh, sorry, no, that's a soft bracket, not a modulus bracket. Okay, so it's a well-known fact that I can, that the modulus of two things multiplied together is the modulus of this one times the modulus of this one. So I can rewrite that as 1 over the modulus of h times the modulus of this integral x to x plus h of f of u minus f of x dx. It's also well known that the modulus of an integral in this way, that the modulus of the integral from x to x plus h of f of u minus f of x dx is less than or equal to the integral from x to x plus h of the modulus of f of u minus f of x dx. Right, so why is that? Why is this formula true? Well, the intuitive reason why it's true is that, say I have some arbitrary function, say it's a positive function, then if I integrate this and then take its modulus, it will be exactly the same as if I integrate it, the modulus, because the modulus function won't change it, and all the values that I'm adding up effectively are positive. Whereas if I have some negative bits as well as the positive bits, then the negative bits and the positive bits will cancel out when you take this sum, and then when you take the modulus, it won't take account of the fact that some of them are cancelled each other out, whereas if you take the modulus of all of them, it'll make it all positive, and then you'll just be adding up those positive numbers, and that'll be bigger than overall doing that. So effectively, it's because whenever you whenever you look at the upper and lower Riemann sums, taking the modulus of a function will increase both the upper Riemann sum over any dissection, and will either increase it or leave it the same, the upper Riemann sums and the lower Riemann sums. So both sort of shift to the right, and therefore the overall integral shifts to the right as well, or it stays the same, but it never goes down, is the point. So we can conclude that. Therefore, and if the function is continuous, and we're using that, sorry, I didn't put that as an initial condition, but if the function is continuous, oh no, it doesn't need to be, does it? Let me just think about this. No, it doesn't need to be continuous, sorry. Or does it? Just trying to think now. No, it does need to be continuous. It does, yes, sorry. If the function is continuous, and I'll explain why it needs to be continuous. The function is continuous. Then we can make this arbitrarily small, can't we? Then okay, so let me revise the definition of continuity. I was thinking that all it needed to be was bounded, and I will explain to you why it needs to be more than bounded. Okay, so if the function is continuous, so what's the definition of continuity? So give me a function f, this is continuous. So f is continuous, continuous at a point x, continuous at a point x. So this is our point x. It means that so this has a value f of x. You take whatever epsilon ball you like, so take all the points within epsilon of here, epsilon, and basically you need to be able to find me a delta ball here, delta ball, so this is delta, such that all the points within this delta ball, so all the points in here are mapped onto the codomain somewhere in between this epsilon ball, and you can do that for whatever epsilon. So for all epsilon greater than 0, there exists a delta greater than 0, such that if U is an element of the ball or around the point x of size delta, it implies that f of u is an element of the ball around f of x of size epsilon. So you have to be able to find the delta such for all epsilon. So basically it's saying however close you make this, I can find you a point, a ball of some size around here such that they're all contained within here. So it's basically saying by making this arbitrarily close, I can make this in the codomain arbitrarily close. Okay, so if f is continuous at x, then let epsilon be let epsilon be greater than 0. I can pick an h, a delta, let's say, a delta greater than 0, such that if modulus of h is less than delta, then it implies that modulus of f of u minus f of x, this should be modulus of f of x plus h is less than epsilon. So let me just explain what I've just done. So up here we have this integral here. So we have our function. Let me draw a picture because it's always best. Here is our value x. We have some h. We do not know whether h is positive or negative, but for argument's sake I will draw it positive. I am integrating along here, but because of continuity, I can for any epsilon you want around the point f of x here, I can pick an h. Such that I can find a delta such that if my point is within that delta, so let this be delta, if my point is within that delta, it will be mapped into here. So if I make the h small enough, because the h is arbitrary anyway, then it will be within this delta ball, and all the points that I'm integrating over will be within the delta ball. So all the points I'm integrating over, the u, which is an element of x to x plus h, so that's all the points I'm integrating over. So if u is an arbitrary point in these things I'm integrating over, then f of u minus f of x will be less than epsilon if I make mod of h less than delta, and I can do that because h is up to me. So by continuity there will exist an h such that if it's within there, there will exist a delta such that if it's within there, it's within the epsilon ball, and then I just make the h so that it's within the delta ball, so that all the points I'm integrating over are within the delta ball. Okay, so do that, and then I can be assured that f of u minus f of x is less than epsilon. So, therefore this integral up here, all of these points in here are less than epsilon, so this is less than, is less than epsilon times the distance over which it's integrated. So effectively what I'm saying is that if I draw a little picture here, that I've got some value which they're all less than, and basically the area underneath the curve will be less than the area of this box here. So this is the value they're all less than. The area under the curve is clearly less than the area of the box, so it's less than epsilon over h. Okay, I should put there modulus of h rather than yes, because otherwise if it's negative you might run into difficulties there. So we'll put modulus of h. So it's true that it's less than or equal to epsilon times modulus of h, because if h is positive, then modulus of h is the same, and if h is negative, then the value of the area is clearly going to be less than epsilon times the modulus of h. Okay, so I can now take this expression here, and this expression here, and this expression here, put it all together, cancel the modulus of h, and I therefore get that this here is less than epsilon if if I pick modulus of h as I did to be less than delta, where the delta ball was the ball for continuity. So basically what I've shown is that by making h small enough, I can assure you that this is within epsilon, and therefore I've shown that that the limit of this quotient is equal to f of x. That I can make this distance arbitrarily small by making the h arbitrarily close, and therefore that it's true that this does converge to this. And that's the proof of the first fundamental theorem of calculus stated here. Thank you.